Friends, welcome to my channel. Dhanesh here. I am going to discuss about quantum teleportation. Before getting into quantum teleportation, let me give an idea about teleportation. See, teleportation is the hypothetical transfer of matter or energy from one point to another without traversing the physical space between them. It is a common subject in science, fiction, literature, film, video games, and television. To understand a quantum teleportation, we need to understand quantum entanglement. Quantum entanglement is an uncanny phenomenon observed at the quantum scale or atomic scale, where entangled particles stay connected so that the actions performed on one of the particles affects the other, no matter the distance between two particles, even at a distance of light years. Quantum teleportation is a process in which quantum information can be transmitted from one location to another with the help of classical communication and previously shared quantum entanglement between the sending and receiving location. Quantum information means the exact state of an atom or photon. Quantum teleportation depends on classical communication, which can proceed no faster than speed of light. It cannot be used for faster than light transport or communication of classical bits, while it has proven possible to teleport one or more qubits of information between two entangled quanta. But this has not yet been achieved between anything larger than molecules. Quantum teleportation is not a form of transportation but of communication. It provides a way of transferring a qubit from one location to another. Quantum teleportation was coined by physicist Charles Bennett. Quantum teleportation was first realized in single photons, later being demonstrated in various material systems such as atoms, ions, electrons, and superconducting circuits. The latest reported record distance for quantum teleportation is 1400 km by the group of Jian V. Pan using Messier satellite for space-based quantum teleportation. Next, we will discuss on quantum teleportation protocol. The prerequisites for quantum teleportation are a qubit that is to be teleported, a conventional communication channel capable of transmitting two classical bits, and means of generating an entangled EPR pair of qubits. Transporting each of these two different locations, A and B, performing a Bell measurement on one of the EPR pair qubits, and manipulating the quantum state of the other pair. An EPR pair means Einstein-Fedosky-Rosen pair is a pair of qubits or quantum bits that are in Bell state together. The Bell states, a concept in quantum information science, are specific quantum states of two qubits that represent the simplest examples of quantum entanglement. The Bell states are a form of entangled and normalized basis vectors. We will discuss about the experimental results. Work in 1998 verified the initial predictions, and the distance of teleportation was increased in August 2004 to 600 meters using optical fiber. Subsequently, the record distance for quantum teleportation has been gradually increased to 16 kilometers, then to 97 kilometers, and is now 143 kilometers set in open air experiment in the Canary Islands done between the two astronomical observatories of the Institute Autophysia de Canarias. There has been a recent record set as of September 2015 using superconducting nanowire detectors that reach the distance of 102 km over optical fiber. For material systems, the record distance is 21 meters. Researchers have also successfully used quantum teleportation to transmit information between clouds of gas atoms, notable because the clouds of gas are macroscopic atomic ensembles. In 2018, physicists at Yale demonstrated a deterministic teleported C0 operation between logically encoded qubits. We are going to discuss about bracket notation or Dirac notation. It is one of the most important concepts in quantum mechanics and quantum computing. Bracket notation is a standard notation for describing quantum states in the theory of quantum mechanics, composed of angle brackets and vertical bars. It's introduced by Paul Dirac. Paul Dirac was an English theoretical physicist who is regarded as one of the most significant physicists of the 20th century. Dirac made fundamental contributions to the early development of both quantum mechanics and quantum electrodynamics. Let's do the implementation for teleportation. Let's assume that Alice wants to send quantum information to Bob. Specifically, suppose she wants to send the qubit state. Let me write the ket vector for that. This entails passing on information about alpha and beta to Bob. There exists a theorem in quantum mechanics which states that you cannot simply make an exact copy of an unknown quantum state. This is known as the no cloning theorem. You can watch my previous video to understand more about no cloning theorem and no deleting theorem. As a result of this, we can see that Alice can't simply generate a copy of the ket vector psi and give the copy to Bob. We can only copy classical states, not superpositions. However, by taking advantage of two classical bits and an entangled qubit pair, Alice can transfer her state psi to Bob. We call this teleportation because at the end, Bob will have psi and Alice won't anymore. To transfer a quantum bit, as discussed, Alice and Bob must use a third party to send them an entangled qubit pair. Alice then performs some operations on her qubit, sends the results to Bob over a classical communication channel, and Bob then performs some operations on his end to receive Alice's qubit. I have imported NumPy, the quantum circuit, quantum register, and histogram, everything I have imported. Let me run this piece of code. Here the protocol uses 3 qubits and 2 classical bits in 2 different registers. Let me run this. Yeah, fine, it's working. A third party creates an entangled pair of qubits and gives one to Bob and one to Alice. The pair the third party creates is a special pair called a Bell pair. Bell's theorem asserts that if certain predictions of quantum theory are correct, then our world is non-local. Non-local here means that there exists interactions between events that are too far apart in space and too close together in time for the events to be connected even by signals moving at the speed of light. The third party creates an entangled pair of qubits and gives one to Bob and one to Alice. The pair the third party creates is a special pair called a Bell pair. The Bell states are four specific maximally entangled quantum states of two qubits. They are in superposition of 0 and 1, that is, a linear combination of the two states. Let me run this. Let me run this script. You can see the output here. Here the protocol uses 3 qubits and 2 classical bits in 2 different registers. Say Alice wants Q1 and Bob wants Q2 after they part ways. Hadamard gate is also known as H gate, which is one of the most frequently used quantum gates. Hadamard gate can be used to convert the qubit from clustering state to uniform superimposed state. Hadamard gate is a single qubit operation that maps the basis state, that is ket vector 0 to 0 plus 1 by root 2 and ket vector 1 to 0 minus 1 by root 2, thus creating an equal superposition of the two basic states. This is the truth table for Hadamard gate or H gate. Let me write the script for that. Here you can see the method, definition Alice underscore gates, and you have the protocol uses 3 qubits and 1 classical bits in 2 different registers. You can see it here. Let me run this script. Yeah, you can see the output here. We have created the Bell pair. Step. Alice applies a measurement of both qubits that she owns, Q1 and the ket vector psi, and stores the result in 2 classical bits. She then sends these 2 bits to Bob. That's what we are going to do now. Let me run this. Yeah, it's working fine. The output, you can see it here. You can see the script here. So in this script, what we are doing is Alice applies a measurement to both qubits that she wants, Q1 and the ket vector psi, and stores these results in 2 classical bits, and then send these 2 bits to Bob. That's what she is doing. You can see the first step, this protocol uses 3 qubits and 2 classical bits. After that, she is creating the Bell pair, then use barrier to separate steps, and she is sending it. That's the third step. Next, what we are doing is, in the fourth step, Bob, who already has the qubit Q2, then applies the following gates depending on the states on the classical bits. 0 0 for do nothing, 0 1 he will apply the X gate, 1 0 apply the Z gate, and 1 1 apply the ZX gate. You can see the script here. The function takes a quantum circuit QZ and classical registers, CRC and CRX to decide which gates to apply. Then the bell pair, then the barrier, then it's sending, and we are drawing the circuit as well. Let me run this script. You can see the output here. So in this piece of code, as I discussed, Bob, who already has the qubit Q2, then applying the gates X gate, Z gate and ZX gate. That's what we are doing in this script. You can see it here. The script, you can see it here. And we have got the output here. It's the output. We can see from the output the Alice qubit has now teleported to Bob. We are writing the script for how to simulate the teleportation protocol. First, we will test the protocol on a quantum computer. So here we will initialize Alice qubit in a random state psi. This state will be created using an initialize gate ket vector 0. We use the function random underscore state to choose psi for S, but psi to be any qubit state you want. You have the freedom for that. So let me write the script. You can see the output here. Let's create our initialization instruction to create psi from the state ket vector 0. Let me run the script. It's working. So initialize, technically not a gate since it is a reset operation, and so it's not reversible. We call it an instruction. If the quantum teleportation circuit works, then at the end of the circuit, the qubit Q2 will be in this state. We will check this using the state vector simulator. Let me run this. You can see the output. The script is working. What we have done is we have initialized Alice qubit as 0. Then we use the teleportation protocol using the bell pair. You can see it in the script. Then send Q1 to Alice and Q2 to Bob. Then we have done the measurement. After that, we have drawn the circuit. So we can see using our state vector simulator, the state of ket vector Q2 is the same as the state psi we created above. While the states Q0 and Q1, the ket vectors Q0 and Q1 have been collapsed to either 0 or 1. The state psi has been teleported from qubit 0 to qubit 2. I will write the script for. Let me run this. It's working and you can see the output here. From this you can easily understand what I have explained. You can see here our state vector simulator, the state of Q2 is same as that of psi we created above, while the states Q0, ket vectors Q0 and Q1 have been collapsed to either 0 or 1. You can see it here. The state psi has been teleported from qubit 0 to qubit 2. That's the output. QASM simulator we are using. On a real quantum computer, we could not be able to sample the state vector. So if we wanted to check our teleportation circuit is working, we need to do things slightly differently. To initialize instructions, first perform a reset setting our qubit on the state 0. If it then applies gates to turn our 0 qubit into the state psi. So let's do. You can see the script here. As we discussed, inverse initialize gates. That's what we are using here. The above qubit Q0 has been teleported to Q2. If we do this inverse initialization on Q2, we expect to measure 0 with certainty. So that's what we are doing in the circuit here. The output also, you can see it here. So this is the script for that. It's working. You can see that inverse init underscore gate appearing labeled, disentangled on the circuit. You can see here in the circuit, inverse underscore init underscore gate appearing in the circuit. That is shown it here. See, disentangled. Finally, we measure the third qubit and store the result in the third classical bit. Let me run this. Yeah, you can see the output. We have done it, right? You can see it here. Yeah, you can see the output here. So we can see we have 100% chance of measuring Q2, the leftmost bit in the string in the state 0. This is the expected result and indicates the teleportation protocol has worked properly. From this histogram, you can understand that. Thanks for watching. Please like, share and subscribe. Thanks a lot.